Hello, my dear children. If you have found balancing chemical equations to be difficult, this video is for you. I'm going to teach you a very simple method that will allow you to solve any type of chemical equation, no matter how big or how small it is. So why do we need to solve chemical equations? What do we gain by doing so? The obvious answer you all might know is that the law of conservation of mass must be obeyed. Mass must be conserved in both sides of the equation, meaning whatever number of atoms react together, the same number of atoms must form the product. That's great and all, but it is not a very instinctive or an intuitive explanation. Sure, the conservation of mass must be obeyed. It is one of the natural laws of the universe after all. But when you solve a chemical reaction, it is very hard to include the combinations in which the elements combine while solving it. Let me give you a simple example of a very rudimentary reaction. Magnesium and oxygen combine to form magnesium oxide. Let's solve this. Over here in the canvas, we have the given reaction. That is Mg plus O2 gives MgO. So let's take this reaction and write it separately. Mg plus O2 gives MgO. Now, the idea here is to separate the product and the reactants, right? So the products fall on the RHS and the reactants fall on the LHS. So how do we separate it? We separate it by listing down the elements, the number of atoms on the element on both sides of the equation. In our case, there are two types of atoms, which is magnesium and oxygen. Okay. So what number of magnesium atoms are present in the LHS? We have one number of magnesium atom present in the LHS. The same goes for RHS. So one number of magnesium atom are present in the RHS. Now let's come to oxygen. We have two oxygen atoms in the LHS, whereas we only have one oxygen atom in the RHS or the product side. So the idea is the LHS and RHS has to match. The number of atoms in the LHS and the RHS has to match, or the number of reactants, number of atoms in the reactants and the number of atoms in the product must match. So we have a mismatch when it comes to oxygen here. What can we do to solve it? You can multiply the number of oxygen atoms by 2, where? In the RHS side. Let's just say we multiply 2 in the RHS. That is, we write 2 in front of the magnesium oxide, the compound that is formed as the product. Now, my question is, what happens to the magnesium here? Does the quantity of magnesium atoms change, or does it remain same? You're of course right. The quantity of the magnesium atoms changes. So the number you multiply the compound with, that is in this case 2, you have multiplied magnesium with 2 and oxygen with 2. So we have 2 magnesium atoms in the RHS and 2 oxygen atoms in the RHS. So that is how the multiplication of a number by a compound works. Now, once again, we can observe a mismatch here, where in the LHS, magnesium atom is only 1, but whereas in the RHS, we have 2 magnesium atoms. How can we solve this? We can solve it by once again multiplying with the right number of atoms that is required. So we multiply by 2 here in the LHS, in the reactant side. Now tell me if the reaction is balanced. Yeah, we have 2 magnesium atoms, we have 2 oxygen atoms, and then the same with the RHS. So this is the process that we are going to follow all along throughout all the equations that we are going to solve. And there is no change in the process at all. Very easy, right? Very easy to understand process. So let's repeat it with different types of equations. I have collected equations in such a way that it is in an ascending order of complexity. We'll solve very easy problems first, and then we'll move on to harder problems. So let's repeat the process by listing out the number of elements in both LHS and RHS. Let's consider LHS first. We have iron, we have hydrogen, and oxygen. So what are the number of atoms then? We have 1 iron, we have 2 hydrogen, and we have 1 oxygen. How about RHS then? So we have 3 iron, 4 oxygen, and 2 hydrogen. So what seems to be the mismatch here? We have the hydrogen atoms balanced, but oxygen and iron atoms are not balanced. So once again, we have to multiply it with the right coefficient. So what is it then? So in the case of iron, there is a singular iron atom in LHS. So it is very easy to multiply 3 in the LHS so that the LHS or the iron atom in the LHS becomes 3. How about RHS then? What happens to oxygen? So since we need 4 oxygen, let's just multiply 4 here and see what happens. If we multiply 4 if we multiply 4 to H2O, we get 8 hydrogen atoms, as we all know, and then we have 4 oxygen atoms. Now, the oxygen atoms are balanced. But still, there is a mismatch in hydrogen because we've just multiplied it 4. What do we do then? We have a very convenient case here. Just like iron, hydrogen is also a singular element. It is not in a compound, which makes it easier. We can once again multiply by 4 hydrogen here in the RHS or on the product side, which gives us an equation like this. So once again, we have successfully balanced the equation of iron and water reacting together to form iron oxide and hydrogen gas. Let's move on to the next equation. Thermal decomposition of potassium nitrate. Let's write down the equation. Potassium nitrate gives KNO2, potassium oxide, and oxygen gas. Now, there is a very interesting thing that is going on here. We have only one reactant, but 2 products. So in this case, we have a word called thermal decomposition. So in the by the application of heat to potassium nitrate, it has split into 2 products. So this reaction, this type of reaction is called as the decomposition reaction. Whenever you apply heat or light or electricity to a given reactant, it splits into 2 products. A single reactant forms 2 products. So let's try and solve this. We have 1 potassium atom. We have potassium, we have nitrogen, and we have oxygen. Those are the types of elements present in the reaction. Now let's list down the number of atoms in LHS and RHS. We have 1 potassium atom in the LHS, 1 nitrogen atom in the LHS, and 3 oxygen atoms in the LHS. Let's move on to RHS. We once again have 1 potassium atom, 1 nitrogen atom, but we have 4 oxygen atoms in the RHS. So we have a observed mismatch here. What do we do then? We try and find the right coefficient to multiply it, to multiply either the reactant or the product, right? So what do we multiply by? We need 4 oxygen atoms on both sides. If I were to multiply the KNO3 on the LHS by, let's say, 2, what do we get? How does that change the equation? Everything changes, right? We have 2 atoms in potassium in the LHS, nitrogen also changes, and of course, oxygen also changes once again. So we have to accommodate it accordingly. Let's see what happens if we multiply the KNO2 of the RHS by the coefficient 2. So the number of atoms of potassium is once again changed to 2, nitrogen becomes 2, and oxygen, this becomes 4, and then we have 1 singular element of oxygen that adds up to 6. So we have successfully balanced the chemical reaction once again. So if you observe here, the key idea is you have to find the right coefficient that you can multiply on both sides with. If you end up finding the right coefficient, more often than not, the equation corrects itself accordingly so that you don't have to identify every single time what coefficient do I have to multiply by. So in this case here, we just multiplied 2KNO3 and 2KNO2 on the both LHS and RHS, and accordingly the equation has adjusted. This is what you'll observe in most cases. Let's move on to the next set of equations. We have a special category of atoms here known as polyatomic ions. So what are polyatomic ions? Polyatomic ions are nitrates, phosphates, carbonates, and such. So whenever we have a polyatomic ion, it is actually easy to take the polyatomic ion as one unit. Let me explain. If we have NO3 appearing in LHS and RHS as NO3, you can consider that NO3 to be one atom instead of considering it as nitrogen and oxygen separately. So this makes the process very simple and easy. But there is a very, very important thing that you have to consider here. You can only use this rule when the polyatomic ion appears as NO3 or PO3 or NH3 or whatever. It has to appear both LHS and in the RHS as the same thing. It cannot change. NO3 cannot appear as NO2 or in a different manner. Then that does not work. The approach does not work. You can only do it when it appears on the same both sides of the equation as the same polyatomic ion. Let's try and solve two equations with polyatomic ions. You'll find it really easy then. Let's consider the reaction between potassium nitrate and barium chloride, which gives rise to barium nitrate and potassium chloride. Right. So let's write down the equation here. Potassium nitrate plus barium chloride. Potassium chloride once again. Right. In this equation, let's try and list down the type of atoms. We have potassium and we have nitrate. Now remember, you can only consider it as one nitrate when it is appearing as the same nitrate in RHS. In our case, it does. So we can consider NO3 as NO3. We also have barium and chlorine. Fine. So let's try and list down the number of atoms in LHS. We have one potassium atom, one nitrate atom, one barium atom, and two chlorine atoms. So how about RHS? In RHS, we have one barium atom, two nitrate atoms, one potassium atom, and one chlorine atom. So we have several cases of mismatch here. So we need to identify the right coefficients to multiply with. Let's start with nitrate. So we have two nitrates in RHS and we need two nitrates in LHS. So let's multiply that with 2. So how does that change the nature of the equation? We'll have two nitrate atoms in the LHS, but we'll also be adding one atom to the potassium. So which makes it 2 potassium. Now we have to consider changing the potassium atom. So how do we change that potassium atom? Once again, multiply it by 2 in the RHS. So which will make the number of potassium atoms in the RHS as 2, but that will change the number of chlorine atoms to 2. Like we saw earlier, a single coefficient added rightly or multiplied rightly will change the entire structure of the equation in the way that we want it to. So we have successfully solved this equation as well. Let's consider the reaction between calcium hydroxide and sulfuric acid, which gives rise to calcium sulfate and water. We'll write down the equation here. Calcium hydroxide plus sulfuric acid gives rise to calcium sulfate and water. So we'll be repeating the same exercise here. We'll list down the number of atoms. Calcium, we have oxygen, we have hydrogen, then we have a polyatomic ion, and which means we have to check if the polyatomic ion is appearing on both sides as the same thing. So SO4 here and SO4 here. Luckily, we do have that condition. So which means we can take the entire unit of polyatomic ions as such. Now let's list down the number of atoms. We have one calcium atom in LHS. We have two oxygen atoms in LHS. For hydrogen, we have 4 hydrogen atoms in LHS and one SO4 atom. Let's go about balancing this. So it seems very simple, right? The mismatch is between only the oxygen and hydrogen atoms. We'll know when we list it out. So we have one calcium atom, we have one polyatomic ion, we have two hydrogen and one oxygen. So the coefficient seems very obvious. All we need to do is multiply by 2. So where do we do that? We multiply by 2 in the RHS or in the product side. What happens if we multiply by 2 here? So the hydrogen becomes, the number of hydrogen atoms becomes 4. The number of oxygen atoms becomes 2. So that is one more equation done. Now we are moving into the territory of a bit difficult equations. Let's consider the reaction between aluminium and copper oxide. We'll write down the reaction. Aluminium plus copper oxide gives rise to Al2O3, aluminium oxide and copper. We'll list down the atoms once again: aluminium, copper, and oxygen. So what is the count in LHS and RHS? We have one atom of aluminium, one atom of copper, one atom of oxygen. So how about RHS? We have 2 and 3 atoms of oxygen, 2 atoms of aluminium, and 1 atom of copper. So we have 2 mismatches here. But once again, we have the singular copper element in the right hand side of the equation, which makes it a bit easier, I suppose. Let's say we multiply. Oh no, the copper atom does not matter here. The mismatch is once again between aluminium and oxygen. So how do we rectify that mismatch? Okay, so we'll multiply the coefficient 2 on LHS. So that makes the aluminium atom to be 2. So the equation is once again balanced. How about copper? Copper is 1. And how about oxygen then? So oxygen, in the case of oxygen, there seems to be a mismatch. So we need 3 oxygen atoms. So we'll multiply 3 CuO on the LHS. So that makes the count of oxygen 3, but it has changed the nature of copper. So copper has become 3 on the LHS. So now we need to alter it accordingly. Since it's a singular atom in Cu, the process is once again easier. All we need to do is multiply 3 to the copper atom on the RHS. Once again, we have successfully balanced the chemical equation. Now we are moving on to the really difficult side of equations. Let's consider this equation between potassium permanganate, hydrogen peroxide, and sulfuric acid, which gives rise to manganese sulfate, oxygen, potassium sulfate, and water. Quite a big equation, but nothing to worry about. We'll once again be following a very similar process that we did in the previous problems. So let's write down the equation. We have potassium permanganate, which is KMnO4, hydrogen peroxide, which is H2O2, H2SO4, which is sulfuric acid, which gives rise to manganese sulfate, plus oxygen plus potassium sulfate plus water. Now you might be wondering why I'm leaving such huge gaps in between each compound. It is to accommodate the value of the coefficient. Right. So the same drill. What do we have here? We have potassium, manganese, oxygen, hydrogen, and we also have an SO4 polyatomic ion, which is appearing as an SO4 polyatomic ion on the RHS side as well. So we'll write that down as SO4. Right. Time to list the number of atoms on LHS. We have 1 potassium, 1 manganese, we have 6 oxygen atoms, and 4 hydrogen atoms. So how about SO4? We have 1 on the LHS. Moving on to RHS, we have 1 manganese, 2 polyatomic sulfates. How about potassium? We have 2 potassium. And how about oxygen and hydrogen? We have 3 oxygen and 2 hydrogen. Okay, where do we begin? let's try and balance the potassium atom here. If we were to balance the potassium atom, we need to multiply on the LHS by 2, which gives us 2 potassium and 2 manganese and 8 oxygen, which once again translates to what? We have 2 into 4, 8. And then we also have another 2 over here. So that means we have 10 oxygen atoms on the LHS. So notice that how multiplying one coefficient changes the entire number of atoms. So we have to be very careful while adding the number of atoms. So how about hydrogen then? So hydrogen, it is not involved. So we have changed 2 of the 3 here, which means we have to change magnesium atom on the other side as well. So magnesium has become 2. We'll add 2 here and we'll multiply the magnesium atom by 2. In doing that, we'll get 2 magnesium atoms on the RHS. Notice that by multiplying manganese, which change. Notice that by multiplying 2 to manganese, the SO4 is also affected. So the SO4 count now becomes 3 on the RHS. So we need to be very careful. So let's move on to balancing the number of SO4 atoms here. So we'll multiply SO4 by 3. Since we have 3 on the RHS, we'll multiply the same thing to LHS. So that makes the SO4 atoms to be 3. So how does that change hydrogen in our case? So hydrogen on LHS becomes 6 and 8. The LHS. Now we have a pretty clear directive. So the hydrogen is 8 and 8 on the left hand side, and then there is 2 hydrogen atoms on the RHS. So let's change that. What do? We multiply it by 4. The water, we multiply water by 4. So that changes the total number of hydrogen atoms to 8. Now the only thing that is left is to balance the oxygen atom. So we need to recount the number of oxygen atoms on the RHS because we just added 4 to the water compound. So which the total number of oxygen atoms on the right hand side is, we have O2 here and then we have 4 oxygen here. So that becomes 6. Now we have to find a coefficient that matches the LHS. So what do we do to add, make it 10? If we were to multiply 4 to oxygen here, what would happen? So we'll have 8 oxygen atoms and 4 oxygen atoms. So that is not the case as well. How about 2 oxygen atoms? That's still 8. So right, so we can add 3 oxygen atoms. So which becomes 6 oxygen atoms, and then we'll have another 4 oxygen atoms here. So that makes the count to be 10. So we have successfully balanced this equation as well. We have found a very reliable method to solve any chemical equation, like we said in the beginning of the video. So no matter how small or how big the equation is, all you need to do is master this method successfully. I have attached a worksheet in the description. Please download it and try out some problems for yourself. In the next video, we'll take a look at the 5 types of chemical reactions. Thank you for watching.